and welcome to Unsupervised Thinking, a podcast on neuroscience, artificial intelligence, and science more broadly. We are a group of computational neuroscientists. I'm Grace.
I'm Alex.
And I'm Jan.
And the topic for this episode is working memory. So working memory is just a form of short-term memory where you can hold something in your mind for a little bit. And we're going to talk about the neural underpinnings of that, kind of the findings about what neurons are doing, the experimental findings. And then we're also going to talk about some computational models of working memory to explain those neural findings. So for this, we read a set of Dueling Perspectives in the Journal of Neuroscience. So these were published in 2018, and they are, I guess, I hadn't seen this in the Journal of Neuroscience before, but I guess they allow people to write a perspective on the same topic, like groups of people that have opposing opinions or thoughts on the topic. So what we read was, the first one is called Persistent Spiking Activity Underlies Working Memory, and the first author of that one was Christos Constantinitis. And then the second one is Working Memory, Delay Activity, Yes, ! Persistent Activity, Maybe Not. And the first author on that was Michael Lundquist. So those kind of offer these two different ideas about how working memory can work, because as it turns out, we're kind of in a upheaval time of the study of working memory. It seems like people are challenging the traditional view, and we will explain what that view is in a moment. We also read a short review called Working Models of Working Memory, which is a list of computational models that have been proposed for understanding working memory, and that was by Amri Barak and Misha Sodix. So we can get into the traditional perspective on working memory that was kind of laid out in the first of these dual perspectives. I keep wanting to call them dueling perspectives, like there's like pistols or something.
Oh, I thought they were dueling perspectives, but they're dual perspectives.
Yeah, they're D-U-A-L as in two.
I saw the A.
Yeah, it would make just as much sense if they were dueling. But I like this concept of publishing arguments in a way, or publishing, explicitly describing disagreements in print. I think it's helpful for the field. Mm-hmm. I don't know how helpful it is for the individual people who do it. I don't know if people get mad at you if you are very explicit.
I think they're signing up for it. They probably enjoy it.
I hope so.
Yeah.
Okay, so the first of these kind of puts forth what I would say is the traditional view of how working memory works. And they also give a definition of it. So they say it's the ability to maintain and manipulate information in the mind over a span of seconds. And I think a common example, like when I was learning it, is the idea that you read a telephone number and then you hold it in your mind long enough to dial it. But that's not a modern example. I feel like people don't have to hold telephone numbers in their mind anymore, because you can just click on your phone and it dials it.
Yeah.
So
I'm not sure if there is a modern example of working memory.
Wow, that's deep. We don't use our working memory anymore.
But I guess what makes working memory different from long-term memory is that usually long-term memory is thought of as changes in the synaptic weights, which changes the attractor of the recurrent network. And working memory should be more flexible than that.
Yeah, exactly. And so we can, I guess, just go directly into the standard model, which is this setup where you are storing something in working memory, and the neural underpinnings of that is that there are neurons that just have maintained higher firing rates or different firing rates than normal for the whole time that is being sustained in memory. And the experimental setup that studies this, or that is used to study this, is usually an eye movement task, where usually a monkey, but I guess they've probably done it in humans too, is sitting in front of a screen, and then there's a flash in a certain location, like a flash of light in a certain location, and then the screen is blank for up to a second or two maybe, and then there's some cue that's given to the monkey that tells it that it should make an eye movement to where that flash happened. So during that whole time, it has to store in its working memory the location of that flash until it's told that it can make the eye movement to that flash. So in a way, it's conceptually simple working memory, because it's just like you were given something and you're just supposed to hold on to it. But the reason that it's challenging is because neurons don't usually keep firing when they're not getting input. So the fact that the flash in that location is not on the screen during the delay period, that's what makes working memory hard, because neurons have to hold on to that information when they're not receiving it. And this neural activity was first found in the 1970s in these kind of eye movement tasks. And so another thing that they talk about is the idea that the neural activity is specific to the thing that's being remembered. So like the location where the flash was, there'll be a neuron that will kind of prefer that location and will fire very strongly when the flash was in that location. And there'll be other neurons that don't fire strongly for that location but have a different location that they like. And so that's the idea of the memory, the neural activity of the memory being specific. But I think in the very first paper that showed this kind of delay firing activity, it wasn't actually specific.
So like all the neurons in that area they're recording from were just firing.
Or the neurons were firing, I don't know if it was all the neurons, but of the neurons that did have sustained activity, they didn't fire differently for different locations. Mm-hmm. So it was just like memory is happening, but they couldn't actually read out what the memory was from looking at the pattern of firing. Right. But since then, there's obviously been a lot of studies where they do find specific patterns. So maybe there's just like they weren't looking at enough neurons or something like that.
I think that's also representative of maybe a trend within working memory, but also within neuroscience in general, looking from like a single neuron tuning curve point of view to a more population, like encoding point of view. But maybe this is something we'll get into later.
Yeah, and another thing that comes up here that comes up a lot in neuroscience is that according to this first perspective paper, this kind of sustained delay activity has only been found in primates. So they found it in single neuron recordings in monkeys and also in humans, single neuron recordings, which is a rare thing to be able to get, but they did find it there. But apparently it hasn't, they said that in rodents, the sustained activity hasn't been found, but like tiling has, where like neurons are firing at different times during the delay.
Yeah, but it was in the same area that, in the sort of analogous area, whereas frontal cortex of...
Yeah, we should say that this activity was originally found and is frequently studied in the prefrontal cortex, particularly in lateral prefrontal cortex or dorsolateral prefrontal cortex. But that's another thing that's kind of up in the air. Some people say that that's not really where the important information is being stored, but like sensory cortex could be storing it. So if you're remembering something visual, there could be areas of visual cortex that show this sustained activity, even though traditionally that's not how we think of sensory cortices as having that kind of sustained activity. So there's a debate about where it happens as well.
But also, I mean, how good is the working memory of mice?
That's a good point. I mean, they can do the tasks that they're doing when they study it, but I think it actually is...
But the training time might be insane.
Yeah. So just because they got to it, if it took them like a year to figure it out and they do it every day and they're super overtrained, like what does that say about, like, are we actually studying a normal working memory system in rodents? I know also this is a point that the second of these perspectives makes in particular. Some people don't like the idea that the storing of a planned motor action, like that shouldn't be counted as working memory. So in the example that I gave where there's a flash somewhere on a screen and you have to remember that location in order to make an eye movement to it, you could say, oh, you're remembering the location, or you could say you're holding on to a motor plan to make an eye movement to that location, which is different than just like storing the information. So in like the telephone number example, you're just like storing the information. Actually, that would be a motor plan too.
But that's a really good point, because like in the very simple example, you could just, I don't know, like have one eye, like you just squint the eye of the side that you have to saccade to a little bit, right? And then this is a really stupid example, but then you don't actually have to have any like working memory, any neural representation of the working memory. I think this is what subsequent experiments were trying to get away from this issue. So I think that's a really good point. Yeah,
but I think there's also like this. I think you can make a similar criticism of saying, okay, you have to hold like the most recent sort of sensory input in the neural activity as well, as opposed to, I mean, if you see like the location of a stimulus or something, that's maybe some sort of sensory input, right? But is it really just maintaining that sort of sensory sort of perception in the sensory cortex, or are you doing something? Are you putting it somewhere, storing it somewhere else that can then be manipulated by some sort of higher area?
Yeah, like the placing working memory in prefrontal cortex makes sense in a way because it's kind of thought of as an interface between sensory inputs and motor outputs. So like the idea that that's where you would find this kind of delayed activity where you're trying to hold on to something about the sensory input in order to use it in the future to make a motor output, it makes sense. And I mean, to me, if it's storing a motor plan or whatever it is, the point is you have sustained activity for a period of time that goes way beyond what like a neuron on its own could sustain its own activity for. So it's like some mechanism is keeping the memory in mind. And whether it's like a memory which is really just like I'm about to move my arm and I'm just waiting for someone to tell me I'm about to move my eyes, it's still a specific thing that you have to hold on to for the amount of time that the experimenter tells you have to. So it feels like it still has, whether it's a motor preparation or like storing something in memory. The examples they give is match, non-match tasks where you see something and then there's a delay and then you see another thing and you have to respond if it was a match or not, because then you can't be planning your motor activity in advance because you have to wait until you see the next thing. So you're really just holding on to the input. But I don't know, in either case there's still something interesting happening that you can hold on to something.
But it's not necessarily happening in PFC or even in sensory regions. Like it could, I don't know. I don't really agree with that. I think that if it's motor preparation, I don't know. I think that's very different phenomenon than working memory. If you already, like, you don't even necessarily have the idea or the image in your head, right? You just have like some tension in like one side of your body or something as you're starting to move. I mean, it's eye movements, so saccades, but
so you're really like pushing it into the body, like. I think a lot of people think maybe like premotor cortex is showing sustained neural activity during that time or something like that.
Yeah, but I'm saying you can't tell. You can't tell if it's it could. I'm using the example in which you're like tensing up one side of your body to show that it's something that you can't dissociate whether it's even happening like really within the brain, except for like the kind of more readout or the more motor cortexy part of it.
Mm-hmm. Yeah, I mean, if it really was. Although I would say even if it were that like your muscles were tensing up in a certain way and that was the only place that it was stored, like what is causing them to be...
Okay, but here's an example. What if like you just put like you just move your right arm like a little bit and then you stop. And then like your whole brain is not doing anything related to the activity anymore.
Yeah, no, I agree. But in the studies of the eye movement task, you're not allowed to move your eyes from the central point until they say.
But you're allowed to move your body.
You would, yeah. So
you're saying that the monkeys are moving their, potentially could be moving their fingers, like saying, oh, like my rightmost finger is like, if I have to move it to the right, I'm just going to do that. And we're not sure if that's actually happening or not.
I'm saying that is a potential confound that you can't get rid of with that type of task, but that goes away when you have a match task. Yeah. And so you might as well use match.
Yeah.
But I think, like, probably that's not what monkey, I mean, they're smart, but like that's kind of...
not that smart.
That's kind of I don't know if that's even smart. That's just like a weird way to solve that. But I think there still is that issue of the motor preparation that I do think is a problem.
Okay. But yeah, so we should say that this kind of delayed activity studies do find it in these match tasks where there isn't a possible motor preparatory part to it at all. So the idea is that there really is something happening in terms of sustaining the information inside your brain and not like moving your fingers to remember it. So maybe to get into a little bit more specifics of what the studies have found. So in the eye movement task, which is still what's used a lot, the first perspective says that up to 70% of all the cells will show this kind of delay activity. And it starts after the visual stimulation is on. And so it turns on and then turns off. And then the delay activity starts. And then it goes away at the time of the eye movement. So it's really aligned with what you would expect to see if this is responsible for storing the memory. And they also said that a quarter of the total population of neurons that they record from has selective activity during the delay, meaning that it's encoding something about the spatial location. And an important thing, at least something that to me is important for talking about like what actually is the functional role of this, how can we say that this is what memory is that there are studies that have shown a strong relationship between this activity and the strength of this sustained firing during the delay with the performance of the animal on the task. So on trials where the delay activity is really diminished or it isn't there, the animal will probably make an error on the task. So like they'll look at the wrong location. They won't have remembered it correctly.
Yeah.
And they also talk about, so basically prefrontal cortex is like a big area, and we frequently just like speak of it as an area, but it has very diverse firing. And so there are parts that might be more inclined to encode spatial information, like when you're looking in a certain direction, and other parts that might be more responsible for like the match to sample tasks, where you have to just like remember something visual. So you have to be careful about which part of the prefrontal cortex you're looking in when you're looking for this sustained activity.
But generally, they find that the sort of most selectivity is in the area that you would expect. So if it's like a task involving moving your eyes to a certain region, then the area of PFC that projects to like the motor region is going to be more selective.
Yeah, so like you can just get the normal tuning of these areas, like what do they normally respond to, by looking at their responses when you just like show an image or something like that, or when the animal is going to make an eye movement or something like that. So you can see what they normally respond to, and that gives you some sense of their function, which is then, related to where you would find the sustained activity.
Yeah.
And we've been talking a lot about like visual stimuli and images, but there's also, people have used different sensory modalities. You can have working memory for auditory cues or for vibration stimuli, like you put a vibration on the finger and you encode the frequency of the vibration. There's also working memory for like rules or more abstract things or categories they talk about, quantities, so just like anything, any part of a task where you might need to hold it in mind for some time, you can probably find neurons, presumably in prefrontal cortex, that have some sort of activity that looks like it's encoding that.
That's, I guess, what I think is one of the more interesting parts of working memory research that I didn't really see much in these two perspectives or the review really. Like in the definition of working memory that you give, it's the ability to maintain and manipulate information in mind over a time span of seconds. And they don't really talk about the manipulation part. They talk about the maintaining part like a lot, and this is what the whole debate is about. But I think the manipulation part is quite interesting and could add like a lot of sort of experimental constraints that I haven't really seen much here, but I guess we can talk about that later as well. But
then isn't the manipulation like a separate question, about a separate cognitive question than the working memory side of it?
Well, if it's rules, if it's like some sort of rule that you have to do, that's manipulating the input in some way, right?
Yeah, but then that's like two functions that the animal has to do. Working memory plus whatever this other cognitive function is.
Yeah, we think of it as two functions, but maybe the brain implements it as...
Yeah, no, that's a good point. Yeah, so working memory could be like, I don't know, what's the word? Like more redundant if it's reproduced in different areas. I think that's a really good point, actually.
Yeah, I mean, and if you're going to manipulate the information in working memory, whatever circuit mechanism that's storing it needs to be compatible with the ability to manipulate it.
Yeah,
so exactly. You do have to be thinking about that when you're thinking of how it could work, is like, how could it be manipulated? And actually this reminds me, so we were saying how this has mostly been found and studied in primates, but actually one of the like very nice findings has come out of fruit flies. Basically the way that working memory is studied in fruit flies is in terms of heading direction. So basically there's like a part of the fly brain where the firing of neurons relates to like the direction that the animal is facing in as it's moving. So it's like you can think of it as like a 360 thing where like whatever direction the animal is facing in, there will be neurons on this like circle that represent the direction it's going in, and it needs that information to navigate. So it knows like I'm walking this direction for this long, so now I'm in this place. So that system has been studied in the fly brain, and it's working memory because you can like have the fly face a certain way and then just like make the room go dark, like take away all its sensory input, and these neurons will continue to fire and continue to represent the direction it's moving. And I think even when it like turns in the dark and stuff, they'll update. And so this updating from like, I'm facing this way, now I'm moving my legs in such a way that I'm going to be facing another way, like that's the working part of working memory. That's the manipulating part of working memory. So you need to have a model that can account for the fact that the activity is sustained in the absence of inputs, but then when it gets the right kind of input that tells it that it's changing its direction, the activity can be moved appropriately.
Where was that?
People from Genelia, I think, right?
Yeah, that was done at Genelia.
I meant where in the fly. Sorry.
Oh, shit.
What does
We're
it matter where in the
obsessed.
fly? I looked it up, the ellipsoid body, and it's in the shape of a ring, and it encodes this ring attractor model.
Yeah.
Some other findings in the primate that lead to, like a causal understanding of working memory. So we've been talking about kind of like neural correlates. It's shown, like you can see that these neurons have this sustained firing during the delay, but does that mean that they're causally important for memory? And so one element of that is the fact that you can correlate errors with the activity, the sustained activity. Like there's a relationship between the performance and the activity. They also talk about, in this first perspective, that if you cool the prefrontal cortex, which in a previous episode we discussed how cooling the brain is a methodology for kind of turning a particular area off. So if you cool the prefrontal cortex, that can impair working memory performance. So that's another kind of causal relationship.
How do they actually cool it, do you know?
There's they don't do it in humans. I mean, they do it in monkeys. There's you should listen to the episode. No, there's like a metal ring that they put in the area, and they just run, not liquid nitrogen, something very cold through it, and it just cools it down. But then it's reversible, so you can do semi-fine timescale experiments where you turn a brain area off and then turn it back on and see what happens.
There's no permanent damage from that? I mean, I guess I should just listen to this, but I'm just out of curiosity. You can take this out. I'm just curious.
Must be so interesting.
I'm sure that there is over time, yeah. If you're freezing neurons and then thawing them. I don't think you have to freeze them completely. You're just slowing down the processes so that they can't really spike. They're working on a totally different time scale. But yeah, I'm sure that over time it's bad for them.
That's cool.
Yeah.
Cool.
Okay, and then so the last bit, maybe a little wrinkle in this story about sustained activity is the fact that it's not actually completely sustained over the period that the memory is being held. So it's not like this neuron goes from firing 3 times a second up to 10, and then it's just at 10 the whole time. So it could be more it starts high, and then it kind of fades, and by the time that the monkey is giving its readout or making its eye movement or whatever, it's almost back to baseline activity or something like that. So there can be ramping up, there can be ramping down, there could just be kind of slight changes over time in the course of the trial, which is it complicates the story a little bit. But in this first perspective, they make the point that a lot of times, even if there's these ramps up or down, the firing still maintains the order such that it's still encoding the stimulus. So you have a neuron that fires high if you get a high frequency vibration stimulus. Even if it ramps down, as it's ramping down on the trials where it has its preferred stimulus, it'll still be firing higher than on the trials where it has its non-preferred. So it's just a uniform ramp up or down no matter what the stimulus is, but the ordering for different stimuli is still preserved such that it's still encoding the information.
Also, even if you have more complex time-varying firing rates than just ramping up or ramping down, there's work by Chklovsky and Shaldrukman that shows that from the decoder point of view, that may not really change anyway. So it could still be representing persistent activity. This is my favorite point in this podcast. So that's why I'm bringing this up again. But
both of the perspectives, I think, reference some study where there's a subpopulation of the neurons that remains similar enough over time that you could always read out from that one. Is that the work you're talking about?
Well, it's so they're saying in these papers that the information could be distributed over the population in a way that if you look at the single firing rates of the neurons, then they might be doing this weird temporal have this weird temporal profile that you wouldn't necessarily associate with the more classic ideas of persistent firing in these really early studies of working memory. So this is a point that was said in the paper that was for persistent activity. This was a point they raised, and this is contrast with in the paper, the dual perspective that was possibly against persistent activity, was saying that on a trial by trial basis, you see these really sparse, not persistent activity on a single neuron level. but I didn't see them respond to that point, that doesn't necessarily mean that at the population level there isn't a persistent representation. And even in the response to that, even though this point was raised in the original perspective, I didn't see that raised again in the response to the other anti-persistent activity paper. And that was my favorite point.
But if there's no like ramping up or ramping down or sort of like temporal dynamic to it, then how is there a limited sort of time period in which you actually can hold something in your working memory? Are there different theories for that? Is it like eventually you just get distracted by another stimulus at some stage and that's the limit of working memory, or is it actually to do with the network dynamics that can only sort of sustain itself for a certain time?
It could be like the time scale of the network in that case, no? Or just the time scale at which you can support that kind of persistent activity.
Like there's like a sudden sort of dying off of the persistent activity that's not seen like in this sort of ramping down, or am I kind of confusing two things?
No, I mean, it's a fair question, and I don't think, like, even in the standard models, even if it were, like, the same thing the whole time, like, the question is what causes it to go away? And I feel like the answer is more something about distractibility. Even if you are just, like, sitting in a dark room, like, trying to remember this for so long, like, your brain is going to be doing other things, and eventually something's going to interfere with that circuit that's trying to maintain that, kind of like by whatever means it's trying to maintain it, there will be something that will eventually interfere.
Yeah, but it's a nice point that the mechanisms of the failure of working memory can also give as much a clue as
because I guess in the other dual perspective, they kind of argue that a weakness of this sort of persistent activity one is that it's, what word do they use? Labile, which just, I guess they really mean easy to perturb due to sort of other stimuli, I guess.
Yeah, so maybe let's switch over to the other one. But I think maybe it would be helpful before we do that to explain a computational model that supports this persistent activity model of working memory. So the very classic, like for decades now, the way that people have understood and modeled working memory is with attractors. And so what that means is basically you have like a neural circuit that the connections between the neurons are such that they kind of self-sustain themselves. So you put in an input, it makes the neural activity go to some pattern, and you can take that input away, and like the neurons, because they're all connected to each other, will keep firing in the appropriate pattern. And so that like completely mimics the experimental findings where you supposedly have neurons that just like keep firing the same way even without input. So that's like the standard attractor model, and like it's defined mathematically, like it's well studied mathematically. It comes from physics and stuff. So it's good then. So it's like you can find a set of weights in a simulation of a neural network where they will have this property of sustained activity and will have attractors. So it's like well grounded in that sense. We know that it's possible.
But isn't that more of like a model of long-term memory, because you need to change the weights every time you have a different like phone number that generations ago they had to remember? Then I don't know. That seems
So attractors they're used to model both long-term memory and short-term memory, because it is the case that like the location of the attractor, the type of firing patterns that it maintains, are defined by the weights. So you have to learn the weights. You have to like know how the neurons should be connected in order to support a certain amount of activity. So you have to get the standard model is that you're exposed to the same thing over and over, and then the weights in the network update as a result of that. And so like things that were like shown together, like if neurons were activated together, they'll fire together and they're wired together, and you can learn the attractors. And then once you do that, you put in an input, the network like goes to this attractor, and you can take the input away and it will stay there. So it's both long-term memory and short-term memory that they're used to model.
But for a short-term, I don't actually know that much about working memory, but for short-term, I usually think more of like bump attractors. Yeah,
but that's still an attractor. So
but it's not like you're not changing the synaptic weights to embed the the attractor dynamics within it.
but you get the synaptic weights from somewhere. Like the synaptic weights have to be a certain way for that to
Yeah,
work.
yeah.
So like a bump attractor is like the heading direction in the fly. Like you have like a ring and you want activity to exist in some place on that ring to represent, like in this case, the direction that the fly is moving in. And you can put like an input that activates some location on this like ring of neurons, if you think of it as like a circle. And then the connections between those neurons are such that they'll keep themselves firing. And usually the way that works is that you have neurons near each other excite each other, and neurons that are a little bit far away inhibit each other. And that's like enough to like keep the activity going at a certain spot on the ring or in the population or whatever. And that goes into the difference between discrete and continuous attractors. So a bump attractor is like a continuous attractor. A discrete attractor is usually what's talked about in long-term memory, and that's like it wouldn't be like on a ring. It wouldn't have any like structure to it. There's just like a pattern of neural activity that can be sustained, and then there's also like a completely separate, unrelated pattern of neural activity that could be sustained. And those would be like two different discrete attractors. Whereas, the continuous ones that are usually more associated with working memory, it's like you can move between them. So in the case of the fly, you have some location, you get an input, and it moves that bump to a different location on the ring. This is very hard to explain without visuals.
Yeah, it's like that the dimension of the continuity gives another dimension along which you can encode the input.
Yeah. But yeah, so the point is just like that's been the standard model for a long time, that it's attractors and we can understand them mathematically and they like do the job, and so like that's what it is. But then recently, I feel like it's somewhat recent, like in the past few years, there have been like experimental findings or like kind of highlighting of things that maybe were there all along that put a wrinkle into this story of like it's all attractors.
So it's easy to sort of visualize or imagine how an attractor model would work well in like the sort of task we talked about with the monkeys, where you have a fixed location, because it's just one thing that you're sort of keeping a persistent activity representing. But then if you're doing a sequence memorization, like I think the perspective sort of cited some things which try to like do these things in attractor models, but I'm not familiar with them, and I imagine it might get kind of tricky to do these things in attractor models, like have multiple bumps and this kind of thing.
So it's certainly the case that the second perspective makes this critique of this kind of attractor model, the critique that it can't hold multiple things at once, and also that it's distractible. The idea that it can't hold multiple things at once, I feel like, is in line with like the historical way that they were studied. They're usually studied in a way where you just have to hold on to one thing and you just have to maintain one pattern of neural activity that would represent one thing. I think the idea that they are subject to distractions is not... I mean, one of the selling points of attractors is that they're not subject to distractions. Like, the point of an attractor, like the name attractor, is that, like, activity is attracted to that point. Like, you can start not at that point and it will go to it. So if you're at that point and you have that pattern of activity happening in the brain and you, like, perturb it a bit via some input, it might go off for a bit, but if it's really an attractor, it's probably going to come back to that point. So it shouldn't be distractible.
I don't really understand the first point, because you could just have like a plane instead of a line, and then you have two, or you just have a hyperplane, and then you have an N.
For multiple
yeah, exactly.
Yeah, and also it really depends on how you interpret the pattern of activity. I could say this pattern of neurons firing means the color blue, or I could say this pattern of neural firing means a blue square in the upper right quadrant of my visual field. Like, what does it mean? What does the pattern mean? And does it encode multiple things is like up for debate.
Yeah, so that's true, but I guess in task where you have to do the ordering as well, okay, how would you... Is the ordering also just another plane in which you...
It just gets higher dimensional.
Okay.
So so like sequence memory and stuff, which is like the telephone example. It does seem like, based on that third paper that we read, the like list of a bunch of different computational models of working memory, it made it seem like basically anything that you could need to do with attractors, someone has worked out a model of how you could do it. And like whether those models are super realistic or fit with the data, I don't know, but it seems like everything has been done, at least in theory. Okay, but so this second perspective, what is it trying to say? I guess the title tells us a lot. They believe in delay activity, but aren't so sure about persistent activity.
Emphatically.
But yeah, so they start out with these critiques from like a more normative perspective, like, oh, well, the attractor sustained activity model, like, it has these flaws. And we've kind of talked about whether those are really actually, like, if it's true that it has those flaws. I would also say, like, working memory isn't perfect. So sometimes the way that they were talking about how the other model is flawed, it's like, well, maybe that's accurate, though. Like, working memory does have a limited capacity, and it doesn't last for very long, and it is distractible to some extent. So, I mean, that's an issue. Like, you really have to get into quantification of, like, is this matching the behavioral data or not? Because you don't want to make a model of working memory that's perfect, because it's not perfect in biology.
Speak for yourself.
Okay, so, like, their thing is that there isn't actually sustained activity from individual neurons on individual trials. So they're claiming that most of the studies that have looked at this have averaged the activity of neurons over different trials, over different, like, runs of the same experiment, in order to find this sustained activity. But if you looked at an individual neuron on an individual instance of working memory, you wouldn't see just, like, higher firing for the whole time. You'd see, like, sparse bursts of firing that have silence in between. That was my understanding of what their overall claim was. And we should say that the first perspective does address this critique.
Population activity.
Right. There's the response that you're not supposed to be looking at individual neurons in a way. That was one response. But they also make the claim that you don't see higher trial-to-trial variability during the delay. And that is like a prediction that would come from this idea that it's like sparse bursts or something. I think that was a claim that they made.
The original authors.
The first perspective, the one that's in favor of persistent activity.
But I think there was a counterclaim then by the other ones anyway. They both sort of disagree on that point.
Yeah.
like many of the points. Like you have to, I guess, read the original papers or something to fit.
That is what I felt through a lot of this. And they also say that, I think not only is it sparse bursts, the idea is also that there are multiple neurons that should be bursting together. So there's like synchrony of neurons. It's not like each individual neuron is doing its own thing. There are synchronized bursts across neurons. And the way that a big part of how they look at it is through analyzing oscillations in the local field potential, which we have an episode on oscillations as well, where we argue about what the local field potential is, if it is anything. But yeah, so they're looking at the frequency spectrum in the local field potential, and they claim that there are changes in gamma, so like very high frequency oscillations that are associated with working memory.
So I didn't really get what kind of changes in gamma they were really talking about. Is it just higher power, or I mean, at one stage I thought like different gamma band, different like subparts of the gamma band had different sort of representations of the working memory, but then that was never really dwelled on. Do you know? Has anyone read?
I haven't read the original.
Yeah.
I can tell you what they say in this perspective, which at one part they say that gamma, I think they're referring to like power in the gamma band. So
Right.
This amount of this gamma oscillations, these high frequency oscillations, is not stationary during the delay period. And their conclusion from that is that means that the firing of the neurons is sparse and periodic. And I don't know why that's the conclusion.
Yeah.
But that was my understanding of what the claim was.
So I think it was it's about like the sort of circuit they had, I guess, which they showed it in a model that like if we have this sort of what you talked about, sort of sparse transient neural representations in a model, then we expect high power gamma, and this is what we see as well, or something.
Yeah, there were a few references to like, yeah, this is what would be predicted if so and so, but I can't actually understand the direct link between the idea that gamma is not stationary. They say it waxes and wanes, and that means that it's periodic. Because to me, if it's periodic, wouldn't you like want an analysis of the frequency to be stationary? Like the thing itself is oscillating, but the frequency should be stationary if it keeps oscillating at that frequency. So I don't know if it's like gamma isn't stationary, but other bands are, and so it's oscillating at a different frequency. I wasn't sure what was meant by that. Oh, and they also talk about, so their thing is that there's like these bursts and it's oscillatory, and a benefit of that is related to this idea of storing multiple things at once. So they're saying that you can multiplex in this way of doing working memory, where at different phases of the oscillations, at different points of it, you could be encoding a different thing. So they say that one way of thinking about it is that there'd be gamma oscillations, like high frequency oscillations, where a different thing is encoded at each point of that oscillation, and then that's like riding on top of a slower, longer oscillation that repeats the thing. So it's like if you have to remember like 4 things, you're just like 1 2 3 4 1 2 3 4 1 2 3 4.
Right.
So you have like each thing has its own part in a high frequency, and then it gets repeated on this lower frequency.
That has a certain element of intuitive sort of. I can see that happening in the brain, I guess.
But so the thing that I didn't understand exactly, like I understand conceptually that would be a way of encoding things, but then the mechanism of how that happens, they make reference to this idea of synaptic changes that happen. Yeah. So like standard attractor models, the synaptic changes are like slow time scale. They're like how you learn something. And then when you're holding it in memory, they don't really change. In this model, it's like every time you repeat it in your memory, it's like causing some like flash change in the strength between neurons such that it can be repeated again.
Yeah.
It's like each time this phase of the oscillation comes around, the fact that there's this trace left in the synaptic weights, that's going to like reactivate this particular memory.
Presumably it's like short-term potentiation.
Yeah.
Yeah, okay.
Yeah. So but that is a question that comes up. I think the first perspective raises this critique that like the time scale of synaptic plasticity, like how fast the synapses can change, doesn't really align with the time scale of working memory. That's their claim, that it's not fast enough.
Really?
Like,
I mean, short-term plasticity rather can be quite fast. It's like hundreds of milliseconds. Is that not the time scale of working memory?
That seems right to me. I think that they were making reference to like short-term plasticity on the scale of seconds, so maybe they're just thinking about a different mechanism.
But the time scale of working memory also depends on like the number of things that you are remembering. So I don't know. I'm not sure that that's predicted by this model.
By the second one.
Yeah.
They say, well, I'm not sure I don't remember if it was the second perspective that says this or the review of the models, but the capacity, like how many things you could hold in your memory, would be a function of like how quickly you can activate each one.
Yeah.
So it would be related to this like oscillatory thing, because they say like in terms of the synaptic weight changes, their model in the second perspective is that you have to keep hitting it with this activity because otherwise the synapse will go back to normal. It's like really fast changes.
Right.
So it's like fast to change the way you want it to, but it's also fast to go back to normal. So that's why you have to keep doing this repetitive oscillatory like hit of the activity.
Uh-huh.
But the thing that I didn't understand is just how you know like what activity to create at each point in the phase to like reactivate. That wasn't clear to me.
Well, it's also an attractor model style thing. I think it's not kept in the dynamics of the neurons, it's kept in the dynamics of the synaptic weights instead. So is that what you mean, or is it something else?
I don't know what I mean because I don't know what they meant. But
yeah.
But no, so the question of like, could this oscillatory thing be also just an attractor, but an attractor where the neurons are like bursty or have some different properties or connected a different way? I think it could be, and I think that the review of the computational models refers to this kind of oscillatory phase-locked encoding as an attractor model. It's like in the section on attractor models.
Yeah.
So I do think that it is an attractor in some way.
Yeah.
But I feel like this second perspective, it didn't speak of it that way, but maybe it's just agnostic to it.
Yeah, I guess. Because they even in the first perspective, they do talk about how synaptic plasticity, in their sense, or in their case, they sort of added it on to their usual persistent activity model and showed that it sort of enhanced the. I'm not sure if it was the capacity or the resistance. Actually, I think it was the resistance to perturbations, for the same reason that the second perspective argued their model is more resistant, which I think is quite interesting. Is that like obviously, if you zap a local network attractor with some spikes, then that perturbs the spikes, but that's not going to perturb the synaptic weights unless it's a very correlated perturbation, I guess.
I thought that it was cool that adding the short-term plasticity made the attractor models more robust. Like, usually when you have to add that kind of biological detail, it's like, oh God, I hope the model still works. Like, you don't even expect it to work better. Yeah. So the fact that you could add that detail, which probably is happening on those timescales, and it still works and it works even better, was pretty nice.
Another thing I thought was also kind of neat was the claim that it was more metabolically more efficient to have this synaptic plasticity sort of way of maintaining the imprint as opposed to in the transient activity, because spikes are more expensive than not spiking, essentially. But yeah, I mean, the spiking activity is quite low anyway, so I'm not sure how much that actually saves, I guess.
Yeah, especially in prefrontal cortex, like the neurons are firing like 4 spikes a second.
Yeah.
You know, and not much more than that when they're encoding things, is my understanding. So yeah, the energy argument, I wasn't as sure about either. Also, well, I don't know, I guess synaptic plasticity can't take that much energy to do, but you have to consider
chemical computation is, I guess, the whole argument for dendritic computation, this kind of stuff, is that it's energy efficient. Although it's kind of jarring from my point of view of thinking about how, like, from a very self-centered perspective, like a computational neuroscientist, I think of neurons as like happy to spike, but synaptic weights take some effort for the synapses to change their weights. This is like a very computational theorist way of thinking about it. So I think those synapses must be exhausted all the time, having to like constantly update and lose it and update it and lose it just to maintain working memory. But presumably that's not how the brain works or thinks about its synapses anyway. Yeah.
Well, it's how your brain thinks about its synapses. But
yeah.
But yeah, I mean, that was the energy argument. I guess I understand the intuition that like spikes are the most expensive thing, like maintaining the right ion concentrations inside and out of the neuron is like really expensive energy wise. But I never feel comfortable with my assumptions about energy costs.
Yeah.
Like, maybe building the proteins that you need to do synaptic plasticity also have some weird energy costs that we're not factoring in, because in neuroscience we just like blanket say spikes are expensive and not spiking is cheap. But I mean, maybe it is true, but I just, you gotta be cautious when you're claiming one thing is less energy than another.
Yeah.
It's not just, okay, this is gonna get into an argument on metabolic efficiency, but it's not just it's not just like the cost of a spike or the cost of anything else, but it's also a ratio between that and like how much information is transmitted in some way, or how much of the computation can be done. So I just have this feeling that in that trade-off, you can always find a cost function that makes you correct as a theorist.
Okay.
That's my kind of squeamishness about metabolic efficiency. Not that I don't think it's a very important subject.
Yeah, and if we're talking also about this multiplexing idea where you're storing multiple things, then the neuron is going to end up firing a lot if at each phase it has another thing to fire. It's going to have a burst or something at each phase for each different thing it's encoding, whereas in the attractor model, the way that you encode multiple things is possibly just through having different subpopulations of neurons where they each encode their own things. So whether having like all the neurons in your network spiking a lot versus having only a subset of the neurons spiking, but you have more neurons in the network, I mean, that's something that have to be considered and worked out in terms of energy costs. So another model that didn't come up in the perspectives but came up, well, wasn't really highlighted in the perspectives but came up in the review, is this idea of like the encoding of the memory would be a pattern of neural activity that changes over time, but it doesn't have to be sustained activity. It just is a model where basically you have a bunch of neurons that are recurrently connected up to each other, and you put in an input, and just as a result of the recurrent connections amongst these neurons, they're just going to like have a trajectory over time that is somewhat specific to that input. So like the trace that this activity follows over time, you should be able to say what input came, even if like the neurons themselves look like they're just kind of going crazy and doing whatever. So that's like a theoretical model that has been put forth. But the issue is then that, like, how do you read out information from that population if it's just kind of like going all over? Like, technically it is following, rules based on what its input was, but it's hard to know what it's encoding if it's like changing so much over time.
Yeah, I mean, I agree that it's not obvious how to read it out, but for some reason I kind of feel like I think it might be easier to do, or there's like more potential for doing like actual computations or manipulations with the representation of the working of whatever you're keeping in memory in the reservoir computing versus some of the more sort of classic models. I'm not sure why I'm saying that. It just feels like a lot of people say that about reservoir computing.
Yeah, there's a lot of work to show that like kind of chaotic or edge of chaos networks, you can do many different types of computations on them.
But has it been demonstrated?
Yeah.
In this context?
For working memory, I don't know. But that doesn't seem surprising. I mean, it's kind of keeping a trace of the input. And I do think that if you have kind of a constrained chaos that's like chaotic, but mostly in some subdimensions, then you could have a readout neuron that didn't have to change its weights in order to distinguish.
Well, that's related to something that they do say in the review, which is that they did a study where they use like completely random connections in this kind of chaotic way, and then compared to a structured network that's like an attractor where the connections between the neurons are like really set to perform a certain way, and then you can also like go somewhere in between where you like kind of train the network to be a little bit more structured. And they say that the in-between area, the like semi-structured network, captures the neural activity the best. So it's like a mix of both and everything.
Yeah, it seems like the fixed kind of attractor network might be good for the kind of tasks that are being studied at the moment, where you have to represent like a number of stimuli that you're already quite familiar with. But maybe when it comes to doing abstract sort of rules or something, then maybe something that's a bit more like reservoir computing might be better. But I'm just saying that. I have nothing to back that statement up.
Yeah,
maybe I do.
Chaotic networks can do anything.
Cool. Okay, well, there you go.
Okay, so I also just want to talk about the psychological element of these two perspectives, like as like a meta conversation about.
You mean the experience of reading them?
The experience of reading them, and also like the way that they were written. So I noticed there were two studies that stood out to me that were cited in both, and so I wanted to see how they were talked about in each one. And so there was one that was talking about like the extent to which you could use the same decoder at different time points in the delay. So like standard model, you should be able to, at any time point during the delay, you should be able to like read out what the memory is, and it should be the same readout decoder that you could use at any time because like the activity is similar enough in the standard model. And so the one that's like in favor of persistent activity like just kind of cites like and it's like studies have shown that like the representation is relatively stable over time, and then the one that was against it was like, well, it showed that like during the very middle of the delay period it would be pretty stable, but still the readout quality was pretty low. So like they were highlighting different things. And then there was another study that was claiming that the gamma bursts were able to predict errors. So like we were talking about how the persistent activity is a good indication of whether the animal will perform correctly or not. And then in this oscillatory bursty model, you'd want to be able to predict errors as well. So they claimed that the gamma bursts could predict errors or were correlated with errors in the perspective that was for that. In the perspective that was against that, they say for that same study that they weren't using gamma bursts during the delay period. They were using gamma bursts when the animal was responding to the stimulus. So like when the delay was over and it was actually giving its response, that's the period of time where gamma bursts were correlated with error, and they were correlated in the wrong direction than what the model would predict, like this understanding of working memory. So that felt like a pretty big omission on the side of the people who were pro gamma bursts.
Yeah. Did we go and check the figures?
I didn't click on any original sources.
Shame.
Yeah, I know.
Neither did I.
You can edit that part out, don't worry.
I think it's important people know. But yeah, we can also talk about the experience of reading it. We were talking before we started recording about the order in which we read it and how that impacted our feelings about it. I read the classical model first, which I was already familiar with, and I was like, yeah, cool, awesome. And then I read the second one, I was like, oh no, they're like really poking holes in it. But then now I've like recovered a bit, and I still like the first model better.
You mean the classical one?
Yeah. And I do think it's also an important question to ask myself is that like, is that bias based on what I was taught first? And how much does that play into, like, stopping scientific progress, that you just like the thing that you were taught first? And also, like, the kind of cleaner model. I think attractors are, like, a beautiful, clean model of how working memory could work. And so I want them to be true.
So I think I read I think it was the same ordering as you, although I had, oh no, I kind of ruined it because I had like a sneak peek of the second one first, but then I didn't read it fully at all. In the first one, I thought, oh man, like there's no way that like the second one is going to be able to recover from this quite thorough takedown. But then I feel like the motivation behind both perspectives is kind of different, and that's not really addressed in the sort of dialogue. Basically, the second perspective is explicitly saying we're not going to try to throw the baby out with the bathwater. Persistent activity is part of working memory, but it's not all that it is, and there are other elements that we need to like update basically. And the first perspective seems to take the attitude that the second one is actually attacking persistent activity as a model, which it kind of is, but isn't doing as much as you would expect if you're reading the first one. So I think it's not really an either or kind of decision for a reader anyway, and it's presented by the first one as an either or decision.
I read the second one first because it had the more interesting title, and I was like, yeah, this seems solid. And then I read the first one and I was like, oh no, they're right. But I think that's just because I'm biased because I like population activity.
No, but I mean, surely there are elements of the second one which are, I mean, like, I really like the synaptic. I'm biased. I like sort of the idea of having this imprint in the synaptic weights that can happen. And I think that could be like a part of it and quite useful computationally. I just don't get this link to the LFP and why that is being so strongly stated. I think there are lots of like positive points about the sort of second model, which are maybe undermined by sort of trying to overstate the LFP link a bit.
Any final thoughts?
So I guess the way I feel about the paper that was critical of persistent activity is that I don't agree with what they were saying about like the temporal aspect of single neurons, because I think at the population level it could still be a persistent representation. But then the point about gamma and beta oscillations, I honestly just don't have the background to be able to assess that very well. So I'm just not sure how to evaluate their model. So I'm just neutral on it, I guess.
Yeah. So that I guess what I liked about the second one is that they sort of also talk about, they're a bit more forward looking maybe in what needs to happen in sort of working memory research maybe. So one thing is that they say that this, much of the evidence for stable coding comes from simple tasks that only require memory for a single item over a blank delay. And I think that's a very important point. So while simple tasks would favor the persistent activity model, the model cannot explain all aspects of the observed activity during richer tasks. I'm not sure about that statement, but I think that's an interesting point. And kind of going back to the original definition, I really think that the manipulation of the computation is kind of underexplored here, and I think that could be a very powerful constraint on sort of working memory models. And actually, I'd imagine that the working memory model just depends on the task, basically. Like in the case of the fly, where it's doing a simple task, the attractor model works very well, but in the case of other things, it might.
Yeah, and I think one of the things that I learned from the working models of working memory review is that there are a lot of models of working memory, and so if there's so many different ways to accomplish this, then it kind of makes sense that there may be different redundant ways of doing this in different, for different computations more specifically, not just within the PFC maybe. I'm not sure.
Yep.
Okay, till next time.
Thanks.
Hey, if you're still listening to this, you must really like us. So how about you go to iTunes or Stitcher and rate the podcast, give us some feedback. You can also go to our website, unsupervisedthinkingpodcast.blogspot.com. You can comment on different episodes, or you could give us ideas for new topics you want to hear about. We would love to hear from you. Thanks.